So today we're going to go over gravitational fields and gravitational field strength. Okay, we've already talked about the force of gravity, okay, and that the force of gravity is the mutual attractive force between two objects. Gravitational field strength is the rate at which those two objects will be attracted to each other, not the amount of force attracting them to each other. So there's a slight difference here. Okay, gravitational force, okay, is how many newtons of force is between the two objects. Gravitational field strength is their acceleration towards each other as a result. Okay, so it's the difference between your weight and the acceleration due to gravity. Does everyone kind of follow me there? Okay, so they are two different things. They are, of course, dependent on all the same stuff. They are dependent on, okay, the masses. They're dependent on how far apart they are and the universal gravitational constant, all of that. Okay, the variables are all the same. Okay, the thing we need to remember here, and we talked about it in satellite motion yesterday, is that gravitational acceleration is the same for all masses, regardless of where they are. Okay, so if I have two objects near the Earth's surface, they will both accelerate towards the Earth at 9.81 meters per second squared. If I have two objects at the distance from the Earth that the Moon is, they will both accelerate towards the Earth at the same rate, whatever that rate is at that distance, okay, even though they have different masses. All things fall at the same rate if they are trapped in a gravitational field. Okay, everybody okay with that idea? All right, so gravity is a field force, okay? Up until now, the only time you probably heard about like force fields and stuff like that was in science fiction, okay? And force fields are science fiction, okay? But field forces, on the other hand, are not, okay? There are many forces that act as field forces. The way a field force is different is that all the other forces we've talked about, other than gravity, are contact forces. That means in order to exert a force, they actually have to be in either direct or indirect physical contact with the other object. Direct being they're actually physically touching. Indirect being they're attached to each other by something, like a rope or a cable. Okay? So there has to be a contact between contact forces. Right? Gravity is not a contact force. I don't have to be in contact with the Earth's surface to be attracted to it. All right? And the same is true for electrical fields and magnetic fields. Neither one of those forces actually requires you to be in physical contact with the source, okay, of the force that's producing the field. Okay? You're just in an area of influence. Right? So obviously both the Earth and the Moon have areas of gravitational influence. Okay? And those areas of gravitational influence overlap each other. Okay? That's why we have tides and stuff on Earth, is because the Moon's gravitational field overlaps the Earth, okay? And why the Moon stays in orbit around the Earth, because the Earth's gravitational field obviously overlaps the Moon. Everyone okay with that idea? All right. What other gravitational fields are affecting us? Really, really big one. The sun, yeah. Okay? The sun's gravitational field is massive. Okay, extends out to the Oort cloud. Okay, if you don't know what that is, that's way past Pluto. Okay, there's the Kuiper belt, Pluto's the Kuiper belt, and then there's the Oort cloud, which is like this other place that's further away. Okay, so anything that stays in orbit around the sun is trapped within the sun's gravitational field, and it extends out a very long way. In fact, for all intents and purposes, any mass has a gravitational field that extends infinitely. It just gets so ridiculously weak that for all practical purposes it's gone. Okay? I'm all right with that idea as well. Okay, so gravity is a field force because it exerts a force without being in physical contact with another object, and gravitational field strength is numerically equal to acceleration due to gravity at a given point. And we know obviously that acceleration due to gravity is different depending on how far from the center of the Earth you are. Okay? And that there are places on Earth where you are going to experience greater acceleration than others. All right. So we got the Earth and we've got the Moon. Okay? They exert a mutual gravitational force on each other, okay, that is equal to this. Big G times the mass of the Earth times the mass of the Moon over r squared. Okay? Everybody all right with that? Yesterday we were setting that equal to centripetal force. Today we're going to set it equal to gravity. And you're probably thinking, what now? Isn't that gravity? Didn't you just spend like the whole last week telling me that that's the formula for gravity? I did. But before we learned this formula, there's another formula for gravity. What was it? M times G. Okay. Theoretically, if I'm standing on the Earth's surface and I do this calculation, I should get the same number I would get if I did that calculation. Agreed? I should. Okay? Theoretically, those two things should come out to the same number. So what I'm going to do is I'm going to use this equality to figure out what little g actually is. How easy is that going to be to solve? Super easy. What do I do with m? Bring it over to the other side. Now, which m is this? That's the trick. Okay? When we go back to gravitational field strength, which one of these is the dominant object? The Earth. Okay, so let's say this isn't the moon, because this number ends up being ridiculously small, and we want to solve for something that's a little more reasonable. Okay, let's say that this is instead the mass of a person. Okay, and we're standing on the Earth's surface. Okay, does that person's mass matter if I'm calculating the acceleration due to gravity? No, because all things fall at the same rate near the Earth's surface, and that number is on both sides, so if I start moving things around, it's going to cancel, right? So I want to isolate little g here, so I'm going to divide both sides by the mass of the person. It cancels, good, because I didn't tell you what it was, and I hadn't really thought up a mass anyway. So now I'm solving for little g. So if I plug in my numbers here, that's going to be 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 divided by 6.37 times 10 to the 6 squared. Okay, what number should I theoretically get here? 9.81. Am I actually going to get that? No. I'm going to get close to it, but not exactly 9.81, because that's an average acceleration due to gravity of all points on Earth. And this number here is the Earth's average radius. Okay, so it makes a bit of a difference. All right, so when I plug this in, pretty close? Okay, 9.83. Actually, sorry, I think I told you the wrong thing. The 6.37 times 10 to the 6 on your formula sheet. Does that say Earth's equatorial radius? No. It says average Earth radius. Yeah. Okay, so we get 9.83. Okay, and that's because at the Earth's equator we're more like 9.78. Okay. And at the pole, we're more like 9.85. Okay, there's a difference there. Okay, about 1% difference between the equator and the pole. So on average, it's more like 9.83, 9.8 something. Okay, it all depends on where you stand. Okay. Now, the other reason that doesn't go out to exactly 9.81 is, did we probably round off a few of the other numbers, like let's say the mass of the Earth, for example, and the radius of the Earth? Okay. Like they're not numbers that have just 2 decimal places. And it makes a big difference when you're multiplying that by 10 to the 24 or 10 to the 6. All right, so everyone follow kind of what we did there. Okay, we calculated gravitational field strength. So if you look on your formula sheet, you'll actually see that formula on there. Okay, big G times M over R squared. Okay, that is how we calculate acceleration due to gravity anywhere. Okay, as long as we know the mass of the object generating the dominant gravitational field, that's the one that goes in there. Okay, we can do this, and we know how far apart the two objects are. right? But this mass is always going to be the larger mass, the one that is generating the dominant gravitational field. Because obviously both things have a gravitational field, but one's kind of caught in the other. And we only see the effects of the big one. Okay, so Michael Faraday was the first person to invent this idea or this concept of a field force, and he did it with a bar magnet. Okay, so he took a bar magnet, which is just a rectangular magnet, and he put it on a piece of paper and then sprinkled iron filings over it. Okay, and what he got was that the iron filings did this. They traced out the shape of the magnetic field generated by the magnet. Okay? They didn't all just go in and stick to the magnet. Yes, a lot of them did. Okay? But what he found was the filings created a shape that looked like this, and they were always directed along these same lines. They would orient themselves, because obviously filings are kind of long and skinny. Okay? And all the filings would line up and align themselves kind of the same way. Right? And he found it didn't matter what size of magnet he used, he would always get this same shape. Well, the Earth's magnetic field looks exactly the same as that. Okay? It's like the Earth is a big bar magnet, and we have this magnetic field, okay, that comes out like that, and that magnetic field then deflects a lot of the really awful stuff the sun spits our way, okay, all the time. Deflects it and makes it go. It's like we have a big shield, okay, big energy shield around the Earth. Okay? This is where the idea of like shields comes from in like all science fiction movies. There's some sort of electromagnetic force field that works like the Earth's magnetic field and deflects high energy particles away from it, slows them down, and makes them cause less damage. Okay? That's where that idea comes from. Because the Earth, the shields are up. Okay? And if the shields ever fall, we'll be screwed. Okay? Because a lot of that really bad stuff will come right through. And here's the scary thing. Research says that the poles right now are in the process of doing something they do fairly regularly, flipping. During the peak of that flipping, the Earth's magnetic field will effectively disappear for a period of time. Okay? And they've seen this in the fossil record as well. The periods when that happens are generally bad. Okay? Like you're going to need some heavy-duty sunblock during that time. Okay? Like walk around encased in chalk, okay? To protect yourself. It's not going to happen tomorrow. Probably. All right, so field forces are forces that act at a distance. Okay? They're an area of influence, and obviously the Earth has a fairly large gravitational field, or gravity well. Okay? Remember I was telling you about that the other day, that gravity can be visualized to be like a hole, okay? With the Earth in the center of it, and everything kind of falls down the hole towards the Earth. Okay. So anything that has mass, like we said, generates a gravitational field. The more mass you have, the bigger your gravitational field, the stronger it is. Okay. So if we look at just the gravitational field of any object with nothing else around, this is what we would see. Okay. The direction of that gravitational field would always point directly towards the center of the mass. Right? And as you get further away, the strength of that field is going to decrease. And it's going to decrease exponentially according to the formula that we looked at just a minute ago. All right, so same things that affect the force of gravity affect gravitational field strength because it's based on that. All right, now for Earth, is it as simple as this? It's not. What else is around? What else is near the Earth that has a gravitational field? The moon. So for Earth and the moon, it looks more like this. Here's the moon, here's the Earth, and you can see that as you move towards the moon, okay, the direction and the strength of the gravitational field of Earth is slightly altered. Right? In fact, there's a point between the Earth and the moon, much closer to the moon than it is to the Earth, okay, where there would be a balance between those two gravitational fields. Okay? Would that be something you didn't have to worry about if you were flying to the moon? Definitely. Okay? Like we picture the Apollo missions as we shot a rocket toward the moon and went around the moon and came back. Okay? It was not nearly that simple. Okay? Yeah, sure, we're in powered flight for part of the way, but most of the way they actually coasted. Okay? They didn't burn the rockets the whole way because that would have required huge amounts of fuel. So they just kind of got going and coasted. And then when they got to this point, they weren't having to fight Earth's gravity anymore. They were actually being pulled towards the moon. Right? They actually started speeding up, and they didn't want that. Okay? They were like slowing down, slowing down, slowing down. Then there would have been this instant where they would have been perfectly balanced and traveled at a constant velocity. And then after that, they would have started accelerating forwards towards the moon. So they actually had to flip the spacecraft over and fire the engines towards the moon in order to slow their descent and actually fall into orbit. Okay? Had they not done that, they'd have just shot right past the moon. Okay? Well, not in a straight line, they would have done this. An unintentional gravity slingshot, okay, that would have, well, ended in their demise somewhere. Okay? That would have been very bad. So what they had to do was account for the fact that once they got close enough to be in the influence of the moon's gravitational field and not the Earth's, that they needed to account for the amount they would accelerate, slow themselves down, fall into orbit. Okay? And then obviously going the other way, okay, they had to accelerate away from the moon, and then as they got closer to the Earth, flip back over again, fire those rockets and slow themselves down in order to perform their re-entry maneuvers. Okay. So, gravitational field of Earth, like we said, is a bunch of vectors. They all point towards the center. The closer you get to the Earth, the bigger they are. Okay? Because the gravitational field strength gets bigger the closer you get. All right, so we're going to go over a few examples here. There's really not much else to tell you about gravitational field strength except this. When I give you a gravitational field strength question, read it carefully. The most common mistake when I give a gravitational field strength question is for people to not calculate little g, but to calculate Fg. And we just finished saying that those two things are not the same. So what I generally do to make sure people don't make that mistake is I put gravitational field strength in the question in bold-faced, italicized, underlined font. Still, people will calculate force of gravity, even though I've done that. And even though I've told you I'm going to do that, okay? People still make that mistake. So make sure you read the question carefully. It's saying gravitational field strength. No, that's what I'm looking for. And the reason I tell you that is because these two things get pretty much the same givens.
One set of pictures, I'm just going to put them there.
Okay,
I
which
don't
period?
know how else to get to the kids before
Which
they
period is that?
leave. Thank you.
Oh, this period. Okay, so you're going to get very similar givens for both questions, and that's why it can be confusing. Okay, you're going to get mass, and you're going to get separation distance and stuff like that. So make sure if it says calculate the gravitational attraction or gravitational force, you're looking for this. If it says gravitational acceleration or gravitational field strength, you're looking for that. All right, so we already did that, so we're going to skip that. Okay, Florence, can you read that? Should I make it a little bigger? I'll make it a lot bigger. How's that? Okay, so for question number 1, you got a satellite orbiting the Earth at a distance of 3 Earth radii from the Earth's surface. Okay, how many Earth radii is the satellite from the Earth's center? 4, right? Because that'd be one more. If it's measured 3 Earth radii from the surface, there's one more Earth radii to the center. That would be 4. Everybody okay with that? Okay. Basically what they're saying is this. Here's Earth. Okay, that's Earth's radius right there. And this satellite was 1, 2, 3 Earth radii from the surface, which means it's 4 Earth radii from the center. Okay. All right, I want you to calculate the magnitude of the gravitational acceleration experienced by the satellite. In other words, the gravitational field strength. So that would be, okay. Give you a minute to try that. All we have to do for the first one is plug in our numbers. Okay, so we're looking at little g is going to be 6.67 times 10 to the minus 11. Okay, so big G times the mass of the Earth, because that's what the satellite is orbiting, and then divide that by 4 times the Earth's radius squared. Okay, so 4 times 6.37 times 10 to the 6. Okay, all squared. Right? When we're looking at that, okay, we're going to have okay, so it should be experiencing a gravitational acceleration of 6.14 times 10 to the minus 1 newtons per kilogram, or meters per second squared. Either one is okay, all right? Let's just talk quickly about those units, okay? Sometimes gravitational field strength is going to be given to you in newtons per kilogram. And the reason for that is, if you calculate little g using our old formula, you divide your weight by the mass and you get little g, that's in newtons per kilogram, okay? Or if you look at the units, kilogram meters per second squared divided by kilograms, the kilograms cancel and you get meters per second squared. Either one is correct, okay? Very rarely does anyone ever write it newtons per kilogram. Alrighty. Let's have you guys try 2 and 3 there. See how you do on those. I often ask something like this as a multiple choice question just to see if people are A, understanding a very important concept, and B, paying attention. What's the mass of a 60 kilogram student on Mars and Earth? 60 kilograms. It doesn't matter where I am, there's the same amount of me, okay? And that's what mass is, and that's just a question that asks, do you remember the definition of mass, okay? And that mass is how much of you there is and how much matter you possess, okay? That never changes. It doesn't matter where I go. I could be at the event horizon of a black hole. I would still only have a mass of 60 kilograms, but I would weigh a lot and be flat, like literally flat, okay? Atomized, really. So that's one that can often come up as a multiple choice question. Okay, students' weight at the equator and on the surface of Mars and Earth. Here's another thing that I often ask. Weight. Is that gravitational field strength or force of gravity? Force of gravity. Weight is the force of gravity. So this question gets thrown in there just to remind you there's a difference between force of gravity and gravitational field strength, okay? If it's asking for weight, that's Fg, right? You would calculate that for both the same way. Fg equals big G times mass 1 times mass of Earth, okay, over radius of Earth squared. And then for Mars, okay, big G times mass 1 times the mass of Mars over the radius of Mars squared, okay? That's what we'd be looking at for weight on both of those, okay? So, in this unit, there's nothing really mathematically difficult, but you really have to pay attention to wording on a lot of the questions, okay? It's crucial. All right. Okay, so a couple of these are worth, I think, just talking about rather than actually calculating. Okay, what would be the weight of a 22 kilogram dog at the surface of Saturn at the equator? All right, now we would need obviously the information about Saturn's radius, but here's the thing with Saturn. Saturn's the least dense planet in our solar system. It's very big and it has a large mass, but it's not very dense. It's made mostly of hydrogen, okay? And if you had a bathtub big enough, it would float in it, Okay? It's actually that light in terms of its density. So when you compare someone's mass on someone's weight on Saturn and their weight on Earth, they're actually not that different. Okay? It's like on Earth, the acceleration is 9.81, and on Saturn, it's like 10.5. Okay? So you'd be heavier, you'd notice that, you'd feel sluggish. Okay? Well, you'd be in a cloud of gas. But other than that, okay, you'd feel a little bit heavier. Not a lot heavier though. Okay? It would be like you just gained 30 pounds. Okay? So you feel heavier, okay? You know, lagging around all that extra weight. Okay? But it would be manageable. Would that be the same for Jupiter? Jupiter's really, really heavy. Even though it's a gas giant like Saturn is, it's way, way, way bigger and way, way, way heavier. Okay? And so as a result, you would experience crushing weight on Jupiter. Okay? Your bones would never withstand it. Like, they would literally snap under your own weight. Okay? They'd have to be much, much stronger, okay, in that case. All right. Gravitational field strength, okay, on the surface of Uranus, okay, it'd be more than it would for Saturn, okay, even though it's not as big as Saturn, it's more dense, okay, and then your weight would change by a little bit, okay. So if we're looking at the answers here, okay, so on Jupiter, you'd have to have bones that are 2.5 times stronger, okay, in order to withstand your weight there, okay, and on Uranus, okay, you'd actually feel, on Uranus, you'd actually feel a little bit lighter. Okay? Because Uranus is so big, but also so light. Okay? All right. Questions on that stuff? All right. Well, for the last time, for 6 weeks, let's clear off those desks, and I will spray them, and you guys can wipe them down.